Good evening, all of you. Is the video and audio clear to everyone? Say. Okay, right. So, let us begin our today's session on linear transformations again. Already we have discussed this concept earlier, so it is nothing but a repetition. So I am going to repeat the whole content of the previous class with regard to linear transformation. Okay. So whoever have the doubt, you can ask it again, or you can clarify your doubts with regard to that class session. Fine. Now, let us go with the definition of linear transformation first. So let us consider two vector spaces U and V over the same field F. So U is a vector space over F and V is a vector space over F. Linear transformation is nothing but a function T from U to V defined by a condition, right? And which satisfies two conditions defined as T of alpha plus beta equals to T of alpha plus T of beta and T of A alpha equals to A into T of alpha. So whenever these two conditions are satisfied by the function T, then we call it as a linear transformation. So you are taking two vector spaces over the same field F, and T is a user defined function satisfying two conditions. Whenever these two conditions are satisfied by T, then we say that T is a linear transformation. And we give different names for T as if T is a function from U of F to U of F itself, that is domain and codomain both are same. In such cases, we call it as linear operator. So what does it mean? T has two conditions and the function is defined from U to U itself. In such cases, we call it as a linear operator. And if T is a function defined from U of F to F, in such cases, we call it as linear functional. So here, the input is a vector, output is also a vector. Here, input is vector, output is a number. So you are pairing a vector into a number. So that is the difference between these definitions. So whatever the name you consider, these two conditions are mandatory and to be satisfied by T. Apart from this, depending upon the domain, codomain sets, we give different names like linear transformation, linear operator, or linear function. Clear to all? Any questions? Say. Is the definition clear? Fine. So, apart from verifying two conditions, there is one condition, we call it as necessary and sufficient condition, defined by So if T satisfies the property that T of A alpha plus B beta equals to A into T of alpha plus B into T of beta, where A comma B are any two numbers in the field and alpha comma beta are any two vectors in the vector space. In such cases, we call it as a linear transformation. So depending upon the problem what we consider, we may make use of two condition method. So if a function is given to you and if you want to check whether it is a linear transformation or not, in such cases you can verify for two conditions. If both the conditions were satisfied by T, then we say that it is a linear transformation. Apart from verifying two conditions, we verify only one condition. If T satisfies this condition, then also T is a linear transformation. So in one way, these two conditions and this one are equivalent. So you can make use of this method or this method while proving the problems. Okay? So please take a note of that. Now let us go for the other definitions too. So one interesting thing is, always we map zero vector to zero vector. Whenever we take two vectors spaces, always it is possible to define a linear transformation. The very simple thing is, you define that T of alpha is equal to 0 for all vectors in the domain. So what it is nothing but the zero map, the zero function. So whenever you define the function T in such a manner, it is always a linear transformation. You can check for the conditions. So the existence of linear transformation is, by default, you can find zero transformations between the two vector spaces. Apart from this, if you define any other transformation satisfying the two conditions, we call it as a linear transformation. Now, the interesting thing is, always the zero vector is paired with zero vector, and for other vectors you can have different images. So the constraint is, if T is a linear transformation, always zero vector is paired with zero vector. In other words, the zero element in the domain is paired with the zero element in the codomain. Further, there is a specific proof. The proof is immaterial, but please take a note of that. Always 0 is paired with 0 from domain to codomain. You please take a note of it. Now let us go with these definitions. What is range, rank, null space and nullity? We go for them again. For range, there is another name called image. Suppose T is a transformation from U to V. So you are considering all the images of U under the function T. So range or image of the function is defined by image of T or R of T or T of U. Whatever the name you use, it is defined by set of all T of alpha such that alpha belongs to U. It is nothing but set of all T images in the domain U. So whatever the element you take in the domain, the corresponding T image will be taken in the image set or range set. Now the interesting thing is, the image set is a subspace in the codomain. So if you observe that if T is a transformation from U to V, R of T is a part in the codomain. So it is always a subspace in codomain. For that you can verify the condition of A alpha plus B beta. That is very easy to verify, that you can do. So please take a note that R of T is a subspace in the codomain. After noting, please tell. Is it okay? Right. Now we go for the other definition, that what is meant by null space. For null space we can have another name, which is nothing but denoted with the symbol n of t and defined as set of all elements in the domain such that whose image is zero element. So if you consider in the domain, you are selecting those elements in the domain here such that for which the image is zero. So n of t is a part in U, and obviously it is a subspace of U. I am going to prove, right? So here let me say a small example, that suppose this is U and this is V. It is a vector space containing 0, A, B, C, D. Let me say it is a vector space. The zero element is 0 dash 1, 2, 3, 4, 5, 6, 7, 8. Now what happens? I am pairing them. So 0 is always mapped with 0. I can do the different matchings now. So if you consider that the range of the transformation is nothing but 0 dash, then you have 1, then you have 2, and you have 5. This is R of t. Clear? And null space of the transformation is nothing but 0, then C. Please understand that R of t is a part in the codomain and n of t is a part in the domain. Is it clear? The distinction between R of t and n of t? Any doubts for anyone? Please tell. All of you clear? Right. Now let us prove that n of t is a subspace in the domain. So if you want to prove that a set is a subspace, it is nothing but it must satisfy the necessary and sufficient condition. So if I able to prove that A alpha plus B beta belongs to n of t, then I can say that n of t is a subspace. So for that I am going to take two vectors, alpha beta belongs to n of t, and two scalars, a comma b belongs to f. Now what happens? Since alpha beta belongs to n of t, as per definition of n of t, from this definition you have T of alpha equal to 0 dash and T of beta equal to 0 dash. What is the condition for this kernel? If you want to say that X belongs to the null space, the condition is nothing but T of X must be 0, because an element will belong to N of T if and only if its T image is 0. So, since alpha and beta are taken in N of T, their T images are nothing but 0. So, if I want to prove that A alpha plus B beta belongs to N of T, the thing is, I should say the T image of A alpha plus B beta must be 0. So, that's why I am considering the T image of A alpha plus B beta. Since T is a linear transformation, you can write it as A into T of alpha plus B into T of beta. Substituting the values there, it is equals to therefore, the image of A alpha plus B beta is nothing but 0. Therefore, A alpha plus B beta belongs to N of T, hence it is a subspace in U. N of T is a subspace in U. Is the procedure clear? How it is proved? Any queries for anyone? All right. Now, let us go with the part that what is meant by rank and what is meant by nullity. As we have observed, N of T is a subspace in U, R of T is a subspace in V. For every vector space, we can find the basis. So, it is possible to get a basis for N of T and a basis for R of T. So, let me say I got a basis for N of T and the basis contains 5 elements. So, dimension of N of T is nothing but 5. So, the dimension of the null space, we call it as nullity. Similarly, the dimension of the range space, we call it as rank. So, what are these definitions? Dimension of the range space, we call it as rank and denoted with the symbol rho of T. And dimension of the null space, we call it as nullity and we denoted with the symbol mu of T. So, nullity is nothing but dimension of the null space. Rank is nothing but dimension of the range space. Okay? Please take a note of them. These two definitions. Now, after having these definitions, there is one important result. We call it as rank and nullity theorem. However, the proof is not important with regard to exam point of view. So, we will discuss its concept, I mean what it says actually, the statement of the theorem. Suppose T from U to V is a linear transformation and U is finite dimensional. Therefore, as per the theorem, it states that So this is nothing but rank T plus nullity T. That's why we call it as rank nullity theorem. If T is a linear transformation from U to V and UV is finite dimensional, then dimension of the domain is equal to rank of the transformation plus nullity of the transformation. That was the statement. So please take a note of that. After noting, please tell. So far we have discussed about the definitions. Let us take some problems on this concept. The first one is, I am defining T from R cube to R square by T of xyz is equal to mod x comma 0. That is my function. So whatever the input vector which is 3-dimensional, I am going to get the output vector as 2-dimensional. Please observe the pattern. So T is transforming a 3D vector into a 2D vector. Did you get it? Say. Now let us verify, is it a linear transformation or not? So here you have two things. One, you can check for the two conditions, or you can check for a single condition. Suppose you are using a single condition. Always n of t contains 0 vector. Please understand that n of t by default contains 0. That is common. Apart from this, we are checking what are the other values in n of t. Right? Are you getting the logic? Yes. So n of t is always a non-empty set. Apart from this, we are verifying, apart from 0 vector, what are the other values are there in n of t. You can have another thing to say, how the 0 vectors becomes 0. There are other ways to say that. N of t is subspace, it must have 0 vector. That's it. I always agree. But the 0 vector belongs to the domain. Yeah, that is also true. Apart from this, if you want to use some properties, you can write like this. So if you want a theoretical proof, this is the theoretical proof for it. How t of 0 is equal to 0 dash. Okay. Right. Please understand that n of t is a subspace, right? How did you say by default that n of t is a subspace? You are verifying a alpha plus b beta belongs to n of t. Before that, you should say n of t is non-empty, right? So let me say the procedure for it. So for this, we prove that for proof of 0 belongs to n of t, this is the part. Okay. Therefore, clear now? Right. So without saying that a set is non-empty, we cannot straight away prove that it is a subspace. For proving subspace, we can make use of the condition a alpha plus b beta. But before that, we should say it is a non-empty subset. That was mandatory, right? Now, let us prove the part that this is the given condition there, and we will verify whether it is a linear transformation or not. So for that, we are going to verify the two conditions. So let us say alpha is equal to x1, y1, z1, beta is equal to x2, y2, z2, and I am going to verify t of alpha plus beta is equal to t of alpha plus t of beta. Is it right or wrong? We are going to verify. So first of all, let us consider t of alpha. So as per t definition, it is nothing but mod x1 comma 0. And t of beta, if you consider, it is nothing but mod x2 comma 0. Now if you write what is alpha plus beta, on adding the vectors, it is x1 plus x2, y1 plus y2, z1 plus z2. So if you consider t of alpha plus beta is equal to mod x1 plus x2 comma 0. Now can you say that t of alpha plus beta is equal to t of alpha plus t of beta on observing the values? In other words, you are comparing like this. Is it right? T of alpha plus beta is equal to T of alpha plus T of beta. Is that correct? The first condition. Say. You agree or not? So one of our friends replied it is not correct. What about the others? Are these two values equal or not? Mod x1 plus x2 equal to mod x1 plus mod x2. Is that equal? You can take a simple example that say alpha is equal to 5, 6, 0. Beta is equal to minus 5, 6, 0. So applying the conditions, is this equal? No. Right? Therefore, the first condition is not at all satisfied, hence it is not a linear transformation. Accepted? Right. Any more queries for anybody? Since the very first condition is not yet satisfied, there is no need to check for the second condition. Please understand. If first condition is satisfied, then we go for second condition. If it is also satisfied, then it is a linear transformation, otherwise not. Okay. So let me take the other problems too. So any more queries for anybody over this problem? Please tell. Now let us take the problem that so for this problem, we need to describe the transformation t from r square to r square as t of 2, 3 equals to 4, 5, t of 1, 0 equals to 0, 0. Clear? So for every problem, whenever a transformation is given, in this you are going to describe explicitly the transformation. In other words, suppose I have two vector spaces here. One is r square, the other one is also r square. I need to find t in such a manner that the image of 2, 3 is 4, 5. And the image of 1, 0 is 0, 0. So in this manner, I need to find the transformation from r square to r square. That was the objective of the question. Okay. So for this kind of problems, we always do that, whether the given vectors in the domain are a basis or not. Whenever the given vectors constitute a basis, then only we are going to describe or find, or in other words, it is possible to find a transformation whenever the given vectors are basis in the domain. Okay. So please take a note of that. whenever you want to define a transformation such that this transformation changes this point as this point, the fundamental criteria there is the domain vectors, whatever you are considering, they must be a basis. Then only you can find a transformation explicitly. Otherwise, it is not possible. Okay? Now, the first thing is we verify that whether it is linearly independent or not. For that, what we need to do, you can calculate the determinant. Since determinant is not equal to 0, it is linearly independent. Apart from this, you can write a linear combination for it. In the linear combination, the scalars are 0, so it is linearly independent. In that way also you can prove, right? This is the shortcut method. Calculating the determinant, since it is not equal to 0, hence it is a basis. So the second thing is, this set spans the domain. It means that whatever the 2D vector you take in the domain, that vector can be represented as a linear combination of these two vectors. It is called spanning. So, what is the requirement here? You take any 2D vector in the domain such that its value is equal to a into 2 comma 3 plus b into 1 comma 0. In other words, every 2D vector can be written as a linear combination of these two vectors. If it is possible, then we say that it is a basis. So let us simplify that. So this gives that so you are going to find the values of the scalars a and b in terms of xy. So I am writing a in terms of xy, I am writing b in terms of xy. So how it comes? So if you solve the equations, the value of a is 3x minus 2y by 3 and value of b is y by 3. I mean, I have a little doubt. This is a, right? So value of a is y by 3 and value of b is 3x minus 2y by 3. So after finding the scalar values, I am going to define the transformation in the following manner. How it is, right? So we have x comma y is equal to a into 2 comma 3 plus b into 1 comma 0. So for this, apply t on both sides. So t of xy is equal to t of a into 2 comma 3 plus b into 1 comma 0. Since t is a linear transformation, it is of the form t of a alpha plus b beta. Applying the condition a into t of 2 comma 3 plus b into t of 1 comma 0. Substituting the image values as well as scalar values, you will get the value as y by 3 into 4 comma 5 plus 3x minus 2y by 3 into 0 comma 0. So this is nothing but 4y by 3 comma 5y by 3. So this is our required transformation. Please check that. So what is the overall procedure here? For the domain vectors, we check and find them whether these are a basis or not. The first thing. Second, if they are the basis, then after finding linear combination, we apply T on both sides for that linear combination. Substituting the scalar values and respect to image values, you will get what is the condition of T. In other words, how T is transforming one value into other value that you are finding actually. Okay? Any questions for anybody in this procedure? Please tell. If you are clear, then I will take the other model. All of you clear about this? You cannot assume, you should prove. That's why you have written the linear combination, please understand. It is nothing but the spanning. Spanning is nothing but linear combination. Please understand, the concept of spanning is nothing but whatever the vector you consider, you are converting that vector as a linear combination of that set. That's it. It is called spanning. Okay? Right. Any other queries? Then let us take one interesting problem on rank and nullity theorem, which is most important. So let us go with that problem first. So the question can be asked in either of the way. So I have a transformation T from V4 to V3. From this, it is evident that you are converting a 4D vector into 3D vector, and it is defined by T of ABCD is equal to that vector. And the question is, you are going to verify rank nullity theorem. In other words, you can say what is the range, what is null space, what is rank, and what is nullity for this transformation that you are actually finding. Okay? Are you clear about the question tag? Right. Now let us go with it. Please understand that as we know that rank is nothing but dimension of range. So you should know what the range contains actually. So what are the values in the range? If you know the values in the range, using them you can find a basis for range, hence you are going to find its rank, because dimension of the range set is nothing but rank. So here what happens, we consider standard basis for the domain. So what is the standard basis for it? Since domain is a 4D space, the standard basis of it contains 4 vectors, which are those. Now please understand that if you apply transformation to a basis, the result generally is a spanning set. So you are getting a spanning set in the range. So this basis will contain a small portion here, the spanning set. So is it understandable, the idea? Right. So if you know this spanning set, we use this and we find a basis. So we use that and we will find a basis for R of t. So let us calculate the images first. So you give me the values. So A, B, C, D is nothing but 1, 0, 0, 0. So if you apply the values are nothing but 1, 1, 1. So can you give me the values here? Minus 1, 0, 1. And here the values 1, 2, 3. And here the values as 1, minus 1, minus 3. Accept it all. Applying the condition of t, say, any doubts? Now using those vectors, it is nothing but a spanning set, we will find a basis for R of t. So how it is to be? So you consider them in the form of a matrix. So you can reduce that into echelon form by applying row operations. So is it necessary for you to write the row operations there? Say, you require that or not? So if you apply the operations, it will come like this. So this is the final thing after applying the row operations. So this is the solution for the first part. So the rank of the transformation is nothing but 2. Please take a note of it. After noting, please inform. If you have any other questions or doubts, you can ask. Right. Now the second part is how to find the nullity. So if you write the definition of nullity, this is the definition of nullity. Since V4 contains all 4D vectors, so you can write that where you can say any questions for this definition of n of t? Please check. The definition of n of t is nothing but set of all elements in the domain for which the t image is 0. Since domain is 4D vectors, set of all 4D vectors such that whose t image is 0. Here 0 is nothing but the 0 vector in the codomain, nothing but 0, 0, 0, the 3D point. Okay, so n of t is nothing but the solution of this thing, because we were saying t of ABCD is equal to 0 dash. So it means that so equating the values, you will get the homogeneous system. So the total n of t is defined by these things. In other words, n of t is nothing but the solution space of this homogeneous system. Is that clear for you? So whenever a question is asked that find n of t, so whatever the t condition is there, you simply equate the condition values in t equal to 0 and solve that equation. That's it. So this is a homogeneous system. We know that how to solve it. Let us write the corresponding coefficient matrix: 1, minus 1, 1, 1, 1, 0, 2, minus 1, 1, 1, 3, minus 3. So if you reduce this in the form of echelon form by applying row operations, you will get the matrix as 0, 1, minus 1, 1, minus 1, minus 2, and the remaining are zeros. So since it is a 4 variable one, so the number of independent solutions are given by so we will take that the variables c is equal to k1 a constant and d is equal to k2 another constant. Okay. So since you know how to solve the respective equations while introducing the constants, so if you substitute the respective values there, then you will get the basis for null space of the transformation. I think you know how to apply the constants there. You agree or not? Right. So if you apply the constants, you will get ABCD as first constant K1 into and second constant K2 into the respective values. Therefore, the two vectors together constitute a basis for the domain, which is nothing but V4. Therefore, if you observe that as you got earlier, rank of the transformation is T and nullity of the transformation T and the dimension of the domain is 4. So you can easily verify the rank nullity theorem. So please take a note of it. Then I want to give the other definitions there. There we can conclude our today's session. The repetition of the class. Later we will go. Shall I proceed? All right. Now let us take the definition of non-singular transformation. Suppose T is a transformation from V to V. Now, if you consider the null space of T and if it contains only zero vector, then we say that T is a non-singular transformation. Why? Because followed by we have a definition that the transformation we call it as invertible if it is a bijection. In other words, the relation between non-singular transformation and bijection is non-singular transformation if and only if it is a bijection. Okay. In order to verify whether the function is invertible or not, we will do like this. We simply calculate its null space. If we are able to prove that the null space contains zero value only, that means other than zero vector there is nothing in that, then we call it as a non-singular transformation and it is invertible. Apart from this, you can verify whether it is a 1-1 onto function or not. So if it is a bijection, then also we call it as non-singular or invertible. Okay, is the definition clear? Now let us take one small problem on this, then we will conclude our today's session. Say, suppose T is a mapping from R cube to R cube defined by T of xyz is equal to x cos theta minus y sin theta x sin theta plus y cos theta comma z. Now the question is, verify whether T is non-singular or not. Verify whether T is non-singular or not. That was the question tag. So we simply apply the definition. Our crime is nothing but we should show n of t contains 0 only. So how can we prove that? I am saying that whatever the vector I take in n of t, it is becoming 0. That means whatever the xyz value I am taking in n of t, xyz is becoming 0 vector. Then what happens? N of t is nothing but singleton 0 only. Accepted? Yes or no? So I will take randomly xyz is any value in n of t. If I prove that xyz becomes 0, then I am done. So from this definition we can say T of xyz is nothing but 0 dash. So if you substitute the values, it is nothing but so from this, if you equate the respective coordinates, you will get that z equal to 0. And the first value is 0 and the second value is 0. So my intention is I should show that xyz value is equal to 0, 0, 0. From this, one part is evident that z is equal to 0. The remaining things are, I should show that x is equal to 0 and y is equal to 0. How? So using these equations, I should prove that x equal to 0 and y equal to 0. Then this task will be completed. So n of t is nothing but 0. Hence the claim is proved. Okay? Is the objective clear? So any suggestions from anybody how to get x equal to 0 and y equal to 0 using the last two equations? From anybody? Please tell any idea, any guesses, etc., etc. Yes. So if you square and add them, the respective equations, you will get the result. So you take this equation, both sides square that. So nothing but x square cos square theta plus y square sin square theta minus 2xy cos theta sin theta equal to 0. Similarly, you add the second equation too. I mean, you square that. So if you square the second equation, you have so if you add them, it gets cancelled. Accept all. Say all of you. Now please understand that x and y are real numbers. Whatever the real number you consider, if you square it, is it a positive or not? I mean, is it non-negative or not? So, x square is a non-negative value, y square is non-negative value. You are adding two non-negative values, the result is 0. So, it is possible only when x and y are 0. Accepted? So only when x and y are 0, then only you can say that x square plus y square equal to 0. Otherwise, you have no chance of saying that x square plus y square equal to 0. If x and y are non-zero numbers, or any one of them is a non-zero value. Agreed? Yes or no? Therefore, we can say that whatever the value you take in n of t, it is becoming that 0. Whatever the value xyz you take in n of t, it is becoming 0. Therefore, n of t contains 0 vector only. Therefore, by definition, the given transformation is non-singular. Fine. Any more doubts for anyone? Right. So this is the complete class of 31st October. So where there is a little lag. Yes, it is invertible. Exactly. It is invertible transformation. Okay. So I think there won't be any repetition of class. So did you watch the recorded video of 30th October? Is it proper or not? Today's class is on 31st October. Agree? This is the whole class. You can visualize the video and relate the content. Both are same. So this is 30th October. You are getting too much lag or little lag? That means not at all understandable. Say. So if it is so, I will take the repetition of the class tomorrow also. Otherwise, we will start a fresh topic, that is solid geometry. So as per your wish, I will go. You want me to repeat that again too? So please tell your queries if you want to repeat. Okay, I will repeat. Tomorrow I will repeat 30th October class, that is basis and linear transformation. Then we will start afresh after Diwali, the new topic. Okay. So let us wind up our session here. Thank you very much. Thanks to all.